Good afternoon, everyone. So this is Yue. I'm a co-founder, CTO of MemVerge. Today, first of all, I would like to thank everyone for joining this session to provide us feedback. Today, I would like to, for the first time, briefly open the hood of the memory machine and show you the architecture of the memory machine, and also discuss a few big memory use cases. But just before that, so just if you are not familiar with persistent memory, especially Optane DC persistent memory, here is basically how it looks like. So first, it's actually a DIMM form factor product that actually also goes into the DIMM slot of the server. All right, so there's a couple of noticeable properties. First of all, it has very large capacity compared to DRAM DIMMs. So it has 128 gigabytes, 256 or 512 gigabytes per day. This basically means you can support up to 4 terabytes PMEM capacity per CPU. Second is that it's much faster than disk or SSD or storage, because it's actually closer to the CPU. It's on the memory bus. So the latency is about 300 nanoseconds versus 90 nanoseconds for DDR4. So basically, it's a bit slower than DDR4, but it's still much faster than storage, which is at the tens of microsecond level, right, for SSDs. And most importantly, this DIMM is actually persistent. So meaning that if you lose the power, actually the data can still actually be there and can be retrieved. But however, it requires some software modifications or using our software like memory machine. Right. Now, if you notice that actually 2 months ago, Gartner actually published a new report named Determining the Data Center Opportunity Created for 3D Point Persistent Memory. So where it actually identifies a couple of interesting areas where they think that Optane persistent memory DIMMs can be actually helpful for the improvement. So this includes, big data analytics, high performance HPC, AI, machine learning, in-memory databases, in-memory data grids, and server virtualization. So for memory machines, for us, we actually have use cases in all of these areas. But today, we just, due to the time constraints, I just want to basically brief touch the in-memory database, AI inference, server virtualization, and the in-memory data grid. So first of all, let's look into these areas, these example areas, and try to see what are the problems that actually becomes our motivation for creating our software. So first, if you look at in-memory databases or in-memory distributed databases, first of all, I'm trying to put lots of data inside the memory. So it's very memory hungry, and it's very costly. So for example, you have to, if you want to use this in the cloud, it's better to buy a larger VM instance with more memory, and which is actually much more expensive than the normal one. Also, another pain point that things that actually put most of data in the memory. So once there's a crash, because the DRAM is volatile, it will suddenly lose all the data in that node. And to recover this, typical practice is actually to load the snapshot living on disk or play a log living on the disk to recover the database, which actually could take a very long time if the database uses lots of memory. If you look at the AI online inferences, so for the inference, one critical criteria is actually to reach very good SLA, which means a very low latency. To make it a very low latency, typical practice is they trying to put the models and the features into the either in-memory database or into other like in-memory data structure, so that the queries or the calculation for inference can happen much faster than using a storage. But if today for the AI models keeps growing and becomes larger and larger, and the number of users that or the training data becomes also much larger. So fitting all this data into the memory becomes much more challenging. And we actually have a customer who is using very large memory servers, and they told us this is very expensive. They cannot buy many because it's just too expensive. And if you look at server virtualization, like virtual machines, right? So more memory definitely means that you can actually start more VMs in the same host, reach higher density and reduce the cost. And also the server for the system admin, they hope to get actually better control or final graduated control on the performance cost trade-off. For example, if for higher priority VMs, maybe it needs performance and should give more memory to that, and the other ones maybe it's just for testing only. Maybe we can give it a very cheap memory, but not the most expensive DRAM to the VM, just to save the cost. And also, if you take snapshots of the VMs and restart from snapshots, could take some time if the VMs actually is a larger VM that uses more memory. So if you look at all these use cases, so there are some commonalities here, right? So if you look at this, we found there are 3 commonalities here. The first one is all these cases need bigger memory and cheaper memory for better performance or lower cost, right? And all these, because they use so much memory for these applications, so restart using the conventional strategy may take a long time. And they might actually, so those might actually limit the application to start using more and more memory because of the failure fault tolerance concerns. So the faster restart mechanism will be preferred to help to protect those in-memory workloads. And third is that we need a more flexible memory management. Let's say you can, for example, is the capability to, give more DRAM to higher critical jobs and also use cheaper memory to those low priority tasks. So all of these, I think these requirements or challenges, we think that they can actually be solved using persistent memory and our software. So let me show you briefly on how we can achieve these 3 requirements. So we have hardware, right? We have CPUs, DRAM in the middle, and we have Optane persistent memory in the DIMM slot. So we have those servers. And then we have those applications just mentioned before, right? Databases, machine learning, AI, server virtualization. And so, and of course, first of all, to utilize those Optane DC persistent memory, we need to install the operating system there. So the Linux with DAC access. The DAC means direct access, allows you to access the PMEM from user space, which is provided by Intel. So these are already, if you have a server that with persistent memory, this will already be there, right? You can start your workload there. Then the question is, how do we provide the bigger memory from this hardware and this existing operating system, and still provide the capability of allow this application to instantaneously restart from the in-memory images, right? The way we do this is, first of all, if we look at the operating system supporting persistent memory today, it will present you multiple memory resources. If you look at let's say CentOS or Red Hat, right? So first, definitely, the system DRAM is already existing, right? So if you do a top, you find lots of memory there. But if you have persistent memory in the slot, you will also find out, especially if they are configured in AppDirect mode, which means that this will enable the persistence. You will be able to find out multiple PMEM devices living under the DAB directory. So those devices are not shown as the active memory. If you use top, you will not be able to see this memory. But they are more like a device. You can see more like a block device or character device living in those directories. And what we do is we first of all we see that. So first of all, there's a challenge here. You can see there's so many devices here, and there's system DRAM, and so it's very hard for user to manage this, right? So the first thing we did is we build our distributed persistent memory engine. What the memory engine simply does is trying to virtualize these separate memory device and DRAM resources into a single software-defined memory pool. So they can create multiple pools. Each pool can consist of some DRAM and some PMEM. And some pool can be created on different NUMA nodes, all across the NUMA nodes. So we support all of these configurations, and on these I can be done just using the configuration files. And once you have these pools created, then on the other side, we also need to be able to allow the applications to allocate memory from us. So in this, to do this, we build our own MemVerge allocator. We call it the TMS. It's short for Transparent Memory Services. So in this Transparent Memory Service, we implement the APIs, functions such as malloc, mmap, all these functions related to acquiring and release memory resources. And we allow the application to use these APIs without changing the application themselves. So once this application can use these APIs, then we further map the object pool or the memory pool created by PMEM machine into the user's application space. And then these TMS allocators will start doing sub-allocation. So you already get larger pool. Then you start doing sub-allocation to allocate the memory for your data structures needed in this application.
At what point in the stack does your software load?
So we are at the user space. It's a user space software.
Okay, so you're obviously the hardware dependencies on the motherboards that can handle the DIMM addressable Optane, but after that, it's just Linux binary running in user space that does the mapping.
Exactly. Okay. Yeah. System demons like this. Yeah. Okay. Okay. So So we don't have any kernel modules. We don't need to install kernel modules. Yeah. All right. So and then once you see that we are already with this infra, we are already be able to make the application allocate memory from us, right? And for this pool that consists of DRAM and PMEM, we're gonna start do the tiering algorithm to put hard data into the DRAM and cold data into the PMEM. So essentially, we know that we are managing the memory for different applications. So we know where exactly the email data are, right? We know those addresses. Now, once we know these addresses, essentially, we create another component called ZeroIO snapshot, because we know where they are. Essentially, what we do is we just send RPC to the memory engine and ask the memory engine to basically mark those as a read-only snapshot, and this will basically complete a snapshot process. That's why we can do the snapshot instantaneously, because we don't actually move the data out of PMEM or out of the DRAM. We just mark them in place and mark them as a read-only and start doing copy on write on that. So I will cover more detail on that. So with this component, the user actually is able to say, okay, please snapshot my application, or please snapshot some pages used by my application. So this allows us to achieve this instantaneous restart for the application without actually, again, changing the application. Now, beyond this, we call these, everything on the left-hand side is our data path. But on the other side, we actually also build a very strong control path for our system. The control path actually can be used to monitor multiple persistent memory engines running in different physical nodes. The control centers actually has no dependency on underlying hardware. So it doesn't need a PMEM, it doesn't need a lot of DRAM. It's very, very inexpensive in acquiring resources. It can run on-prem, and it even can run in the cloud, even if your data nodes actually run in on-prem. And they interact with this data nodes through the RPCs. And through management center, we provide the first of the CLI to allow users to just use the CLI to manage the snapshot, take the snapshot, list all the snapshot or delete, all kinds of management operations. Furthermore, we build a set of REST APIs that provide to users. So the user actually can program to manage it or scheduling the snapshot of the application, or start or shut down the applications on memory machine. And based on these APIs, we further build the web UIs, which Charlie is going to show a demo on. And that web UI actually uses the REST API, and the user can also use web UI to monitor the memory usage, DRAM usage, PMEM usage for each application on each node, and to again manage the snapshot that's taken for different applications.
In the web UI, does a user or admin have access to actually see the memory? Because I'm thinking if I'm able to look inside the memory, right, what are security features around to prevent this? Because then I have the crown jewel, I have the database. So is the web UI more like a passive viewer, or can I actually see what the system sees in the memory?
No, the web UI, you can only see the snapshot names, the process names. The system link can see all the process names and all the name of the snapshot, but none of the users actually can examine the content of the memory, the content inside the memory.
So there's no way to see the raw data.
There's no way to see the raw data. Yeah, okay. And we actually further provide isolation so that different applications actually can use different memory resource. So they don't. So one application will not be able to see the memory content of the other application. Another point on this security is that Intel is actually also pushing out another thing called TKME multi-key encryption for persistent memory. In that case, will enhance the security isolation for applications that are sharing the same persistent memory. So that's incoming for the Barlow path.
So actually, a quick question may kind of build on that. So should I interpret this as each of those TMS processes as kind of different virtual memory spaces for the processes? Is that kind of a way of looking at it?
Correct. Yeah. It's just like the virtual memory process space of each application. You see that this whole system is actually looks pretty complicated, right? And if you are familiar with persistent memory, you know that persistent Intel is already providing some facility or some tools that allows us to users to use persistent memory as a big memory or use it as a persistent memory, right? So then the question is, why do we need to use memory machines? Why do we need to build this complicated the stacks, right? So if you look at so here, let me review the existing tools Intel provides first, and then we'll show you why we are building them. If you look at Intel Optane DIMM, it provides two modes. The first mode is memory mode. The memory mode has a very big advantage is that if you configure the PMEM into that mode, you will see that the server suddenly has a huge amount of memory. For example, in the free command or top, you can see the memory goes to terabytes. So the process, it provides large memory instantaneously. And of course, you don't need to change any applications, the code, to enjoy this large memory. But the drawback is that, first of all, if you configure the memory mode, the DRAM, whatever DRAM you put there, the capacity actually will be hidden. And it's a cache design so that the DRAM capacity will be used as a hidden, be used as a cache tier for the memory. So it's a not tiered architecture, it's a caching. So data actually can live both in the DRAM and the PMEM at the same time. So the total capacity on the memory mode you see will be the PMEM capacity. So in case your server actually has lots of DRAM there, let's say your server has 500 gigabyte DRAM, maybe 500 gigabyte PMEM, then what you will see is you only have 500 gigabyte memory, which maybe you feel a bit lost, on the cost side, right? So because you lose all the DRAM capacity. The other thing is the PMEM is always in this mode is always volatile. There's no way to actually persist the data. So if you reboot the server, the data will be lost, cannot be retrieved back. And the other thing is the DRAM here is a cache. It's actually a shared cache, which means if you have multiple applications, so there are chances that these applications actually get mapped to the same DRAM page cache. If that happens, if there's a noisy application that keeps on running and keeps on accessing the memory, and this will actually keep contaminating or polluting the cache of the other application. And for the other application, you will only be able to see the latency or the PMEM plus a swap. So which will hurt the performance and SLA. And another constraint is that once you configure the memory mode, so the DRAM and the PMEM ratio will be fixed for all the applications. So there's no way to say that this application I want to only use DRAM, the other application I want to use everything in PMEM, and something and the other something in between. So you cannot do that. So all the applications actually are sharing the same fixed ratio, which is not that flexible. Now, the other mode is the app direct mode. So in this mode, so one of the biggest feature is that once you do that, it becomes the Optane memory becomes a device, and the PMEM is actually persistent, just like a storage device, right? You can mount a file system, right? You can map that, and you can actually retrieve the data after reboot by remapping and get the offset and so on. But the concept is that to use it as a memory, essentially you actually have to change your code. Right? You need to rewrite your program using some programming API, maybe like Intel CMDK or maybe our API, but you need to use some APIs to rewrite applications. So that cannot be directly used without code change. So the memory machine, basically we build this, the motivation is that so we want to address all these limitations while still keeping the good features of both modes. So that means memory machine today, we make the DRAM capacity still available. So in our case, it's a tiered memory design, which I'm going to talk about in next, so that the total capacity is actually DRAM capacity plus PMEM capacity. So it's a tiered memory hierarchy. Again, we don't require application to be changed to get DRAM-like performance. And at the same time, we do provide the programming APIs for advanced users to change the application. I will cover both use cases in the next. And because we use a tiered design, the DRAM actually will be unshared between applications. So this actually is a way to mitigate the noisy neighbor issues through the memory resource isolation. And everything here in our software is fast-defined. So actually, user can define the DRAM PMEM ratio for each process he or she launches on memory machine. So this is quite flexible. You can say that something this application can be have and have, or the cheaper application can just use everything in PMEM. So that's doable just through a simple configuration. And the memory snapshot feature, this is a bit unique. It's only available through our software. And most importantly, so we are user-space software. We mainly just rely on the DAC kernel features, which means that we also work with any memory devices that actually support DAC. Okay. So in the next few slides, I'm gonna basically do some deep dive into the basic transparent memory service, the memory allocation features, and also the snapshot features. And we'll show some sample use cases there. Just let me know if you have any questions. First of all, our transparent memory service uses a tiered memory allocation model. So as I just mentioned, so this means that the total capacity is the DRAM plus PMEM. Right? We don't hide the capacity of DRAM and also the hot pages. Because we actually manage the code, the temperature of the pages. We can monitor that, and we'll put the hot pages, the pages that with more frequent access, into the DRAM tier to make sure the DRAM can accelerate those memory access, and we'll put very cold pages into the PMEM. And again, even for these behavior, the caching, the tiering behaviors, user actually can, if the advanced user can actually fine-tune those behavior through the configuration file. So you can define, how frequently you want to evict, or how many pages you want to evict in one batch. You can actually, for advanced user, we recently even push out a very experimental feature that allows users to actually plug in their own tiering algorithm to replace our default algorithm as a plugin module. So in this case, if you really know your workload quite well, you can design your own tiering algorithm and plug into our memory machine, and we'll start using yours. So, we keep on allocating memory from DRAM and PMEM. So, and we're trying to prioritize the critical memory access using DRAM. But if there is a failure to allocate the DRAM, either because of running out of DRAM or other reasons, we'll try to keep the application alive by fallback to use the persistent memory. Right? So, and meanwhile, if we found out it's because of the DRAM is running out, we actually start evicting the code pages from DRAM to PMEM to yield space for the applications. And the eviction itself always has lower priority than the user access. So, which means that if the user keeps on accessing the memory, we'll try to not evict as often as used to be, trying to basically, because eviction will introduce some performance impact. We will monitor the user's workload, and we're trying to evict when it's idle and evict less often when it's busy. And most importantly, as I'm showing on the picture on the left-hand side, different applications, their DRAM tier actually are not shared. So which means that application one that is busy doing writing to the DRAM of to its own DRAM will not likely to have a huge impact on the performance for application two that is accessing its own DRAM pages. So which is not the case for the memory mode that came natively with the Optane. And also you can see, as shown in this picture, different applications actually can have different size for their DRAM tier and the PMEM tier. so which can be made much more flexible. Right? And interestingly, in our upcoming release, we're pushing out a new feature that allows the system mean to actually dynamically adjust the DRAM PMEM ratio without restarting or stopping the application. So imagine you have a VM or KVM running there, and this KVM during daytime is very busy. Everyone is using, is accessing that, doing some calculations. Admin wants to also make sure the performance is good, so it uses lots of very large DRAM size DRAM tier to guarantee the performance. But at night, nobody's using that, right? So running that on DRAM is perhaps a bit wasteful on the resource. Maybe that resource can be used for other offline jobs to use, right? So in those cases, you can actually just use the ZeroIO REST API to essentially to adjust this ratio, so to make it use PMEM only, right? So it's still there, it's still alive, it's still available, but it just becomes a bit slower. Right? Since nobody's using that, maybe nobody cares. And the other feature is we are trying to mimic the memory allocation behavior provided by the kernel, and we are NUMA aware. So meaning that if we found out a new application, let's say it's in NUMA node 0, we'll try to, and it's allocating memory, we'll try to supply the DRAM resource and the PMEM resource from that NUMA node. Once it's moving to another node, we'll try to migrate the pages to the other NUMA node, so that we always try our best to give you the local access to the memory. Because for PMEM, the cross NUMA performance will become more significant, so that we actually spend all the time actually to address those issues. So in the next, I want to give you a few sample use cases that generated from our transparent memory services. The first example is an evaluation using KDB plus benchmark. So if you're not familiar with KDB, so KDB plus is actually one of the important time series database widely used in financial industry. It's mainly for one use case is used for storing the ticks, the market data, and to allow the quants and other analysts to basically apply different algorithms to go over this time series data. And one of the nice the part about KDB is that it's actually tried to put this real-time database trying to put all the data in the memory just for very low latency and for real-time data analytics. So it's a use lots of memory. It's a memory database. So we took one of its official benchmark, which is actually bulk insertion benchmark, which actually emulates the bulk insertion of the market data, the hourly market data into the database, and trying to evaluate this on top of the performance on top of memory machines. So here are the results. The results actually are normalized, meaning that we take the MemVerge results and divide it by the baseline. And this is a throughput. So the higher, the better. And if it's higher than 1, if the y-axis is higher than 1, it means that we are outperforming the DRAM baseline. If it's lower than 1, it means that we're slower than the DRAM baseline. So you can see I'm showing a few cases here. The blue case is basically means that we are letting the KDB to use 1 GB DRAM, and the rest is in PMEM. And the oranges basically shows that we are actually using 400 megabyte DRAM plus PMEM. So to give you the data size, essentially this is a small data benchmark. So the total data size is about a little bit more than 1 gigabyte, 1 to 2 gigabytes. So the first one you can see is that most of the data actually will reside in our DRAM tier. And second, the orange bars correspond to the scenario where half of the data will live in DRAM and half of the data will live in PMEM. And then the gray one is just that we further reduce the DRAM tier size, and until the yellow one, where we only use PMEM for storing all the data for the database. And you can see that if everything almost fits in the DRAM tier, we're actually outperforming, our allocator actually outperforming the baseline DRAM allocators especially if you look at the larger bulk inserts on the right-hand side, we actually provide up to 2 times speed up comparing to the vanilla KDB on vanilla, the memory allocator. And if you look at the right-hand side, the yellow ones, it's not actually that bad for many of the cases, especially you see that for the larger bulk inserts, right? We're perhaps 20 to 30% slower than running everything in DRAM. But if the user, the customer, is not using this actually for really high performance, highly performance critical scenarios, just for testing or offline analysis, maybe this is still acceptable. So the point is not how slow we can achieve or how fast we can be. The point is that our software can allow the user admin to achieve all these points on the trade-off curve just through the software-defined configuration. And you can do this even without, you can do this dynamic changing even without restarting the application itself, just using our command line or REST API to change that in real time without interrupting the application. Okay, so that's the first example using KDB. The second example is we have custom POCs where they want to run the KVMs actually on top of memory machine. So the benefit of running KVM on memory machine is that we are actually allows the customer to basically create a very cost-effective KVM configuration. For example, the customer may want to, let's say, allocate a VM, let's say, with 8 GB or 16 GB memory, and we can allow the system, the KVM VM admin, to say that for this 16 or 8 GB memory, maybe you can use 50% DRAM and 50% of PMEM, or you can you can keep on changing the ratios for the VM for different purposes. Right? And you can still use this feature to actually dynamically adjust the ratios in real time. So we run the KVM on memory machine, and we run many benchmarks. So one of the benchmarks we use is the Unix bench, which is widely used for evaluating the system's performance, Unix or Unix-like systems performance. So here's you can see on the left-hand side in this architecture, the Primo is actually the Primo process allocating memory from us, right? So then we Primo together with memory machine are living in the user spaces. On the right-hand side, we show the Unix bench scores. And interestingly, on the right-hand side, lower up right corner, it lists all the basically the testing cases included in this Unix bench. Basically, trying to exercise all the typical function calls or facilities used by Linux, right? Unix. If you look at the results, right, the DRAM baseline, which is basically running this benchmark without any of our software, it has the highest performance. But if you look at the other cases generated by us, right, we use the PMEM only to run this benchmark. We use all PMEM plus 2 GB DRAM to support this VM, or we use 16 GB to support this VM. You can see the performance actually is really, really close. And so the most interesting part is that using PMEM actually almost does not decrease the performance reported by Unix bench, which is a very good news for this kind of workload. So the third example is what Charles just mentioned in his slides, where in this case, we actually do provide our APIs, memory allocation APIs, to the customer, to allow the customer to precisely allocate memory from PMEM and from DRAM. And through these POCs, we show that memory machine actually can provide orders of magnitude lower latency than the baseline. So here is actually what the customer is using before this POC. So what they have is they have an image recognition framework or platform, which takes the input image, many images in batches, and trying to find the most similar pictures in the database. So the way, in a simple way, basically what it does is when it starts, we'll warm up the DRAM cache by bringing some of the hard features stored in a MongoDB living on SSD into the DRAM. Then during its operation, so it was trying to find trying to search for the hot features to see if there's a match for the input picture. If there's a cache miss, it will send IPCs, using a client to retrieve this data from MongoDB. So once there's a cache miss, right? So then the latencies will become very high because this includes networking, right? The sockets, and also includes the data serialization, deserialization, because data actually is living in a serialized format when it gets stored in MongoDB, and it might first actually be compressed also. So you have to decompress that as well. So with us, we changed the customer's infrastructure to basically to converge the storage and the memory into the same tier, essentially. And then essentially we still put the hot feature in DRAM, but we can actually fit all the terabytes of features in persistent memory. So in this case, if there's a cache miss, we actually can just directly query another native hash table living on top of PMEM. So querying those hash tables does not actually require any data compression, decompression, or serialization, deserialization. And there's no IPC because actually it's living in the virtual memory address space of the application. So there's no IPC required. That's why such changes actually brings huge improvement in throughput and latency. So if you look at latency, where actually the blue ones correspond to the baseline using MongoDB and DRAM, and the red one, the orange ones are from our implementation. You can see that it basically is actually multiple orders of magnitude faster than before, just because we get rid of the IPCs, or get rid of the compression, or get rid of the serialization, deserialization. And as a result, the throughput also gets improved significantly.
What's the space overhead that you need? Obviously, if we're talking terabytes, I mean, if I have to lose a few gigabytes here and there for your stuff, that's not going to hurt too much. But just curious what the ratio is roughly for the space overhead for managing this.
Yeah, we have a few hundred kilobytes of data that we need to basically record for each of the memory pool we create. So that's the main overhead. If we create a snapshot, we also have metadata, again, it's at a level of 100 kilobytes to record the snapshot relationship, the snapshot trees. But that's pretty much it. So if you look at realistic workload today, you'll mostly see the memory consumption by DRAM and PMEM is mostly just for their data structures. But you hardly see our space overhead.
Okay, so it's basically irrelevant when you're doing the sizing. If I ask for a 4 terabyte PMEM space, I'm pretty much getting my 4 terabytes and I don't have to worry about it.
Yeah, correct, almost, yeah. So in the next, I will just also briefly introduce the ZeroIO snapshot feature. So it is an approach where we're taking that we think that almost does not require storage. Well, I'll show you why I put almost there. First of all, there are a couple of important features here. It's instantaneous. Right? Why does it instantaneous? Because it doesn't, when we take a snapshot, we just mark the memory in place, read-only in place. So we do not actually move the memory data to a storage device. And restore also, we restore in place, right? So we don't move the data. And when we take the snapshot, so here's just some more technical details. When we take a snapshot, we want to guarantee that the snapshot is persistent. So the persistence for our system means two things. First thing is we need to flush whatever in the DRAM cache, right? We have DRAM tier. If you enable DRAM tier, so we need to flush the DRAM tier back to the PMEM so that we can persist those parts that is in the bolus memory. The second thing is to make sure that everything is persistent in PMEM, we also need to flush the CPU cache so that to make sure that the CPU cache, the change in the CPU cache actually gets flushed back to the PMEM. So this will, if both succeed, this will mark the persistence completion for the snapshot. And this again will take much shorter time if comparing to copy this data to a storage device. And also the format of this snapshot actually is the name, it says it's a hash table. That's actually the hash table there. It's not a serialized or deserialized format living on the storage system. Okay. And once the first snapshot is taken, typically you will see that if you look at this snapshot, the space consumed will almost equal to the space you allocated for your data structure, let's say for your hash table, for example. Then, and we'll mark this as read-only. So which means in the following, we'll start doing copy on write. So just like, how the fork works in Linux, right? You do the copy, start doing copy on write for the fork process to have a read-only copy of the memory of the parent process. So to do this, after the first snapshot is taken, let's say there's a new update. So we'll basically just we'll know which pages you're updating. Then we'll just copy those pages into a new page and record the delta there. And we will take a second snapshot. The second snapshot will only include the new data, new update, and also plus a pointer, point back to the parent snapshot. And you can do, if there's another update, we recorded another delta there, and the snapshot. So each snapshot, basically, a following snapshot will only record the differences. Second thing, a snapshot in our system actually can be cloned. What do I mean by that is that, let's say you have already taken a snapshot. You can actually instantaneously, within less than 1 second, you can actually clone multiple applications that are actually sharing the same snapshot. So what is the main motivation behind this, right? Think about you have an in-memory database that it's a memory bound, right? So you have enough CPUs there, but you cannot, and let's say you want to do some load balancing for the database, meaning that you want to create more instance, more replica of the database. But in this server, because it's memory bound, you run off of DRAM, so that although you have enough CPU, you cannot start more instances. But with this feature, you can actually take a snapshot, just clone from the snapshot, which will bring up multiple instances at the same time. And these instances will actually share the same piece of memory until some cloned instance gets new updates. Right? So in this way, we actually can allow the workload to actually increase the CPU utilization with the same amount of memory. The other use cases, of course, you can see like it can be used for sandbox testing or debugging. Right? Let's say you found a problem in the production, right? You want to take a snapshot, and maybe you want to clone another one so that this one can be cloned for the developers to just look at the problem, right? So this will not interrupt the master copy. And all these are done instantaneously. The snapshot also today can be replicated from memory to memory. So meaning that if you have application running on server 1 and you want to take a snapshot, right? And then let's say you want to actually migrate the application to another server, or you want to restart the same application in another server, you can use our tool to actually replicate the snapshot to a different server. And this server actually can live in the same data center or can even live on the cloud. And once the snapshot gets replicated to that node, you can actually clone or restore the snapshot instantaneously from that node. So this is actually a recaption of this live migration, right? Which is very interesting for VMs or container environments. Right? And we can provide this kind of HAs for it's another way to do the HAs for the snapshot.
Just a quick question on that scale of things. Yeah. When we're talking about snapshotting chunks of memory around, I'm imagining my unit of portability is got to be a virtual machine at this stage. I can't be shopping around a process from one server to another server. Or can I?
Yeah. So in this way, actually, it's a process. It's actually you can migrate a single process to another.
Right. So Eric, to your surprise, we are managing at the process level.
Yeah.
Okay. I'll just let my brain quietly explode or melt. I'm not quite sure which will happen first. So what does that look like at the OS layer? Like I'm having a really hard time visualizing. It's like I have my MongoDB process running, and then I just have another copy of that process running in another machine.
I think if you wait for 10 minutes,
we'll get into the demo. Okay, great.
In Charlie's demo, you will see each application and how do we deliver a memory machine to each application, and that's a unit where we take a snapshot. Right?
Yeah. We're talking the process level, Linux process level, portability.
Process level, yes.
Okay, thank you.
Yeah.
and by the way, that's why I think it's a new paradigm of managing applications.
That changes a whole bunch of things right there. Yeah.
So this is actually, in particular, it's friendly to the containers because containers actually process running namespaces in a high level view. So it will be helpful to move the containers faster.
So is there a way to dump some of these memory spaces for, say, like forensic purposes and kind of investigative purposes? Is that so? I have a chunk of memory, I need to pull it out so that I can put it through some memory analysis tool for security or other purposes?
Exactly. Actually, this morning we actually have an internal discussion on this, and we chat with another collaborator, which brought up this use case. Actually, yeah, I think that it's very interesting. Yeah, if you have any we can talk more about this offline if you.
I think security forensics could be a good use case. We have got multiple inputs recently. We haven't developed a use case on that, but I think it's a strong possibility. As you can see, what we're presenting is kind of the base foundation. There are many possibilities on top of this. We're just scratching the surface.
Yeah, basically we can provide APIs to security researchers. Just look at this deltas, right? That you can open up the deltas. Then trying to see if there any delta introduces like a pattern, memory pattern for, let's say, ransomware, for example. All right. Okay, so let me continue. So another feature where it actually is related to why I said we almost does not require storage is that this one actually requires storage. You can actually export the snapshot outside of the memory. So let's say, for example, you want to release some space, or you want to get rid of you want to backup or archive some very cold snapshots, you can do that by do the snapshot export function we have to export to a storage device. And this can be a shared storage, can be a AWS S3, can be a SAN, can be a distributed file system, right? And of course, you can, once you export it, you can import this back to different servers, different environments. So this is just a slower way to do the snapshot replication in this way that you can actually restore from that. Okay. Okay. So and the last one I want to mention is today. So we showed you the results for snapshot single node applications, right? But if you look at this in-memory database and other applications, today rarely you will find that these applications are single node applications. Most of them, Redis, Hazelcast, other TensorFlow, Spark, they are all used in a distributed way. So people are running those in multiple nodes and they work together as a cluster. So today, we also support snapshot of the clusters application. Such as, we'll show you an example that we can snapshot the Hazelcast cluster, and we today also can snapshot a Redis cluster as well. I will show you some results on that. Okay. So first of all, I will go back to the KDB because Charles actually talked about the Redis. So I will briefly mention the Redis, but so let me go back to the KDB. So the one pain point of the KDB is that if there is a failure or if there's a crash, or if you want to restart the KDB to make it to go to the same state you want, the only way to do that is to actually let the KDB to replay the log that's generated on a file system. So if the KDB is huge, then it takes forever to actually replay those logs one by one, because they actually replay and you need to apply those operations one by one, right? It's a sequential operation. So with memory machine, we can just basically take a snapshot of the KDB that is running in the production environment, and we can just restart that KDB without snapshot instantaneously within less than 1 second. So here is actually evidence. The y-axis plots basically the mainly just the restore time, right? The x-axis correspond to different cases where the KDB has different sizes. So the maximum we did is a 600 gigabyte KDB instance, which is a very large instance. We compare basically two cases. The first case is basically our memory machine snapshot, and the second case is actually just a baseline restore by reading the logs from SSD, NVMe SSD. And you can see that there are blue bars in the first two, and the other ones do not have the blue bar results because the other two the memory is too large. It's way larger than the DRAM, so we're not able to do the DRAM experiments there. If you look at the first one, for 380 gigabyte database, for the baseline, it takes about 510 seconds, which is a bit less than 10 minutes to load this 380 gigabyte data back to the KDB. And for us, it takes about 2 seconds to snapshot, and it takes about 1 second to restore the database back into the operating condition. And similarly, you can see that the performance of our snapshot restore does not degrade when the data size increases. This is just because, as I mentioned, when we take snapshot or restore, it's mainly just metadata operations. We never move the large data. So that's why it keeps constant. For 600 gigabytes, it still takes about 1 second to just restore the whole database. So the next example is the Charles just mentioned, restore a more than 300 gigabytes Redis instance that has 300 million keys inside. This is a huge Redis instance. And for the baseline, to restore that, Redis has to load this so-called RDB, which essentially is the on-disk snapshot, load them back to the memory. So for this instance, Redis takes about 15 minutes to load everything back to the database. Then after that, only after that, it will start being able to accept new requests. So when you restart the Redis, you will see the login message saying it's loading the RDB, the database is not ready. And suddenly, okay, everything's done, then it's ready to accept the request. For us, it's just a half second to bring back this Redis. And you will see that Redis after half second is already be able to accept the request and to do the read and write. So this is about 1,500 times faster compared to the conventional scheme. The last example I want to show you is a Hazelcast in-memory data grid cluster restart. So this is actually one use case we tested within Test and San Paulo, Charles just mentioned, which is one of our paid customers. In this case, you can see that we have something called ZeroIO snapshot coordinator. The coordinator actually can coordinate snapshot activities between multiple nodes and for the cluster application. Let's say here, for this example, you have a 2-node cluster, right? 2 physical nodes, and each of the nodes, Hazelcast is basically it's an in-memory database, right? Running on top of our memory machine TMS. And the snapshot coordinator can actually receive the command from the user and basically notify a coordinated snapshot to happen simultaneously for the nodes living on different for the Hazelcast nodes living on different physical servers. And also, of course, once the snapshot is done, the snapshot also coordinator can also coordinate the restore activity. So let's say you want to restore one single node, or you want to restore the whole cluster. You can do that also instantaneously through the coordination. So here is actually a performance measurement we did to compare our restore performance with the conventional way to restore the Hazelcast cluster. The conventional way is actually called hard restart. There's a hard restart feature that's in Hazelcast cluster. Essentially, it's very similar to other in-memory databases. Essentially, it's basically based on snapshot loading and the log replay. And those data will have to live on a file system, on storage system, in a serialized format. So the blue bar, the y-axis shows the restart time of the 2-node Hazelcast cluster. The x-axis shows different. We tested different cases, and each case has a different total memory usage. So up to 131 gigabytes in total, right? So the minimum we tested is 22 gigabytes. So the blue bars correspond to the baseline where they put the data in a PMEM backed file system. So remember, with the app direct mode, you will be able to mount a file system on top of PMEM. So you actually can use it as a storage file system device. You put files there, and of course, maybe you will have a memory speed file system to load the data back in to restart. And the green bars correspond to putting the data in a local NVMe SSD backed file system, and both are using XFS. And different there's a deep green and a light green. So these correspond to the internal parameter they are using. So the different parallelism. So basically, 12 parallelism means that using 12 threads in parallel to load the data, on the disk back to the memory. So the more threads you use, perhaps the more performance on the restart you will get. But it will saturate after a certain point, right? And for us, our results, our performance is the orange one. That is almost not visible. So again, in this case, we're again just orders of magnitude faster than these two baselines that are using PMEM file system and MEME file system. And again, the reason is that we don't need to move any of the data, and there's no such parallelism for us because for us we don't move data. What we do is simply just a metadata operation. This is simply done using one single thread. So we don't need to use lots of CPU to move those data between the memory and the storage device.
I do have a question. I'm going to throw this out there. Being a backup guy, and I think Charles and Yue, we talked about this before. Being a backup guy, snapshots are not backups, but if you catalog snapshots, they potentially can be backups. So what's the future look like, either through partnership or from your own well of knowledge and technology prowess to think about that from a high availability, from data protection perspective?
So first of all, today we do support restore from the snapshot and then replay the tail log. So we actually have a demonstration for Redis. You can restore from our snapshot and continue replace the log left over there. And the other thing is our coordinator today, actually one interesting part is not only you can coordinate cluster snapshot, they actually can coordinate snapshot between the memory and the storage. Let's say your application has a state in storage. The application also has a state in memory. The snapshot coordinator can actually take a snapshot in memory. They also call the storage appliance, the API, to snapshot the storage device, the storage state also. So that we can jointly restore them together.
Yeah, and then to answer your question directly, we have not integrated with the backup software yet, but I think that's definitely a possibility given that we have a snapshot. And this snapshot is in memory, but it can be moved to any storage device just to stage there for a backup software to pick them up to join the backup workflow as well. So it is an interesting direction. We have not done it yet. It could be somewhere on the roadmap.
You guys didn't see this, but I tweeted out when Yue was presenting. The answer is yes. It seems whatever you ask MemVerge, the answer is always yes. You just proved my point right there.
Well, some of them is now, some of them is
later, right?
Yes.
So
Thank you.
Could you give us an idea of something that your solution isn't right for?
Yeah.
Maybe something people have tried to use it for or asked about, and you said, no, please don't make us do that. Something like that.
Yeah. So let me start, and you can add to my answers. So I think that clearly there are So let me just first saying that we are, I hope it's obvious we are very excited about what we do. It's a huge opportunity. I think we are doing something that was never done before. But at the same time, I think it's going to take time because it's such a new paradigm that it takes time for people to adjust to this new paradigm. So it's definitely going to take time for the world to change around it. And let me just add to that. I think one of the panelists, one of the delegates, was mentioned about cost. There is still a big gap between the big memory solution and the storage solution. So while we are excited about the future picture where all applications running out of memory, that's not going to happen soon. Storage is an order of magnitude cheaper, and it's just for the scale of the data that the storage is continue to be needed. And our approach right now is how do we coordinate our big memory with storage, such as snapshot, so that they can work well together. So So I think if you're looking to using us and just throw out all your storage boxes, not quite yet. This is first of all to enhance the really the memory capacity and enhance the memory side of things. So I hope those kind of give you some initial things, so sort of where we see the boundaries of ourselves today.